On a branch of a big tree sat a little bird, Peter's friend. All is quiet, chirped the bird gaily. Just then a duck came waddling around. She was glad that Peter had not closed the gate and decided to take a nice swim in the deep pond in the meadow. Seeing the duck, the little bird flew down upon the grass, settled next to her, and shrugged his shoulders. "What kind of bird are you if you can't fly?" he said. The duck replied, "What kind of bird are you if you can't swim?" and dived into the pond. They argued and argued, the duck swimming in the pond, the little bird hopping along the shore. Suddenly, something caught Peter's eye. He saw a cat crawling through the long grass. The cat thought, "The bird is busy arguing. I'll just grab her." Stealthily, she crept towards him on her velvet paws. "Look out," said Peter, and the bird immediately flew up into the tree. while the duck quacked angrily at the cat. From the middle of the pond. The cat walked around and around the tree and thought, is it worth climbing up so high? By the time I get there, the bird will have flown away. Grandfather came out. He was angry because Peter had gone out into the meadow. It is a very dangerous place, he said. If a wolf should come out of the forest, what would you do? But Peter paid no attention to his grandfather's words. Boys like him are not afraid of wolves. But grandfather took Peter by the hand, he locked the gate, and he led him home. But no sooner had Peter left the forest than a big grey wolf did come into the meadow. The cat climbed up the tree. The duck quacked, but in her excitement, she jumped out of the pond. But no matter how fast the duck tried to run, She couldn't escape the wolf. It was getting nearer and nearer, catching up with her. And then he got her, and with one gulp, swallowed her. And now, this is how things stood. The cat was sitting on one branch. The bird on another. Not too close to the cat. And the wolf walked round and round the tree, looking up at them with greedy eyes. In the meantime, Peter stood behind the closed gate without the slightest fear, watching all that was going on. He ran home, got a strong rope, and climbed the big stone wall. One of the branches of the tree around which the wolf was walking stretched out over the wall. Grabbing hold of the branch, Peter lightly climbed over onto the tree. Peter said to the bird, "Fly down and circle around the wolf's head. Only please take care that he doesn't catch you." The bird almost touched the wolf's head with his wings, while the wolf snapped angrily at him from this side and that. how the bird did worry the wolf, how the wolf wanted to catch him. But the bird was cleverer than the wolf, and the wolf simply couldn't do anything about it. Meanwhile, Peter carefully made a lasso and letting it down. He caught the wolf by the tail and pulled with all his might. Feeling himself caught, the wolf struggled wildly, trying to get loose. But Peter tied the other end of the rope to the tree. And the wolf's jumping only made the rope around his tail tighter and tighter. Just then, the hunters came out of the woods. Following the wolf's trail and shooting as they went. But Peter, sitting in the tree, said, "Don't shoot. Birdie and I have caught the wolf. Now help us take him to the zoo." And there. Just imagine the triumphant procession.
Okay, now it's time for us to start the lesson. Right. So now we are coming back to the lecture notes unit 10, which is concerned with the rotation of the objects. I hope you could hear me. Okay, one student is still trying to get into the room using the reading room, so I have to tell him. Okay, not meet him right now. So at here, we have basically finished the lecture notes of chapter 10, which is an introduction to the rotational motion. At the beginning, we talk about the kinematics. Of course, we have introduced the concepts of the angular rotation to start with. I will explain it, the quiz later during just before the break. Okay, I think I better start the lecture right now. So we have the introduction of the rotational motion in the unit 10, starting with angular displacement, velocity, and acceleration. These are the parameters to be used. And then we describe the motion by using the kinematic equations. So we assume there is a uniform angular acceleration, and in that way, we could perform the calculations for the motion of the rotating objects. In particular, we are talking about objects that are rigid, so it will not change in shape. Particles are always moving in the same radius from the axis of rotation. So that is the idea of the kinematics. And we need to kind of define the motion in another way. Unlike the linear motion, we have the mass, which is the inertia of the object in the linear motion. In a rotational motion, we have the objects that are rotating, and the inertia is defined by the moment of moment of inertia, which is dependent on the axis of rotation. So that is something quite different compared with the mass. Mass of an object is basically, sorry, just a minute. It is basically independent. It is basically independent of the configuration or the distance or arrangement of the axis. In the case of a rotation motion, however, axis is very important. So we have to define the axis before we can obtain the moment of inertia. We talk about the moment of inertia, how we could calculate it. Conceptually, it is the sum of the mass of individual particles times the square of the distances. And then if you have a multiple of the particles, it would be then integration of the equation. But if you have objects that are rotating about the center of mass and you move the axis away from the center of mass in a parallel manner, then you could make use of the parallel axis theorem to calculate the moment of inertia. In this table, you could see that the moment of inertia, most of them are going through the center of mass. And if you have the rotation that is not about the center of mass, then we would have to recalculate the moment of inertia. One of the methods is by the parallel axis theorem. You move the axis parallel to the original one that goes through the center of mass. And in that way, the moment of inertia could be calculated about the new axis of rotation. So we have seen the deviation, and we have used it in one example of calculating the moment of inertia about the end of a rod. And we also talk about the torque, which is the equivalent of force in the linear motion. We have the torque, which is dependent on the size of the force and also the distance in which we apply the force on the object from the axis of rotation. So it depends on the distance r. Finally, it depends on the angle in which you apply the force. If the relative orientation, if the angle between the force and r is phi, then the actual torque is related to the sine phi. So you could consider this term in two ways. In one way, you could consider it to be the component of the force perpendicular to r. So using the daily experience, use the common sense experience, when you have the force applied along the r, you cannot turn a spanner. Only if you have the force perpendicular to r, then you could have the turning effect from the torque. And another way to see it is to consider the perpendicular distance of the force from the axis of rotation. So this one, which is d, it is the perpendicular distance of the force vector from the axis of rotation, which is equal to r times sine phi. So in both ways, you would obtain the equation, the torque equals to r times f times sine phi. The torque, it is a vector. Strictly speaking, you have to define the direction of this vector by something called a cross product. On the other hand, to make the thing simple, we confine ourselves to the case of rotation in a plane, rotation in a two-dimensional plane. So it is either clockwise or anti-clockwise. If the force would generate a rotation that goes anti-clockwise, we consider it as a positive torque. If it goes clockwise, we consider it to be a negative torque. That would make things slightly simpler. Although strictly speaking, you have to use the vector concept. But once you go to the vector concept, it becomes very difficult or complicated to understand, because on one way, this is rotation, and on the other way, the vector, it is just an arrow, just like shown in the diagram. So how you figure out the two things may be difficult to understand. So let us just try to consider the torque to be generating rotation in the clockwise or anti-clockwise sense. For the time being, that should be sufficient. And we have also discussed about the energy of a rotating system. So basically, the work done in the equivalent format, we could consider the work done to be due to the torque causing an angular displacement of an object. A torque causing the rotation of an object by a certain amount d theta, and this is the work done. Just like the case when you have a force applied to an object and cause a certain displacement. Force times displacement to generate the work done, we can only consider component of the force parallel to the displacement. For the case of a rotation, at least for us, it is simpler because the rotation is all in the same plane. So there is no any angle between them. Either it is positive or negative. So the things are simpler. And we have a kinetic energy for the rotating object. It is equal to 1/2 times I omega squared. The equation form would be equivalent to that of linear kinetic energy, 1/2 mv squared. For most of the cases, this would be used independently. So you have a rotating object about a certain axis, then the rotational kinetic energy about that axis, it is 1/2 I omega squared. But if you have a rolling object, then the situation is slightly more complicated, because if the object is rolling, you could consider it to be a combination of two effects. The first one is the rotation of the object about its center of mass. So it is just like you hold the wheel on the axis and it rotates. So there must be rotational motion. There is a rotational kinetic energy. On the other hand, if the object rolls, then the center of mass for the object actually moves as well. So there are two energies. There are two kinetic energies. One is the rotational kinetic energy, and the other one is the translational or linear kinetic energy. The total kinetic energy would be the sum of the two things. Sum of the rotational kinetic energy about the center of mass plus the translational kinetic energy for the center of mass. In particular, when you have the object that is rolling, the center of mass is moving with the speed or velocity that is related to the angular speed of the rotation. That is the case of the rolling. If you have the object that's slipping, then that would be another story. So in an object that is rolling, the two things are related to one another. The linear motion for the center of mass is related to the angular motion of the rolling object. So this is what we have seen so far. And when you try to count the number of things we have seen in the linear motion and compare it to the rotating motion, you will find that there is still one property that has not got the analogy, and that is the linear momentum. We talk about the kinematic equation. Of course, we have the kinematic equations. And we talk about the inertia. So in the linear motion, we have the mass. In the rotational motion, we have the moment of inertia. Kinetic energy, we have the equivalent. Force, we have the equivalent, which is the torque. Here. And we also have the kinetic energy as well. So finally, what we are left behind is what we are going to talk about in today's lesson, and that is the angular momentum. the idea of the angular momentum, it is kind of, once again, similar to the case of a linear momentum. You have objects that are interacting. So in between the objects that are interacting, there would be internal torque. Now you are talking about objects that are rotating. So that is not force anymore. We talk about torque. And so if you have a internal torque, the torque generated by one object would be equal and opposite to the torque acting on the other object. So kind of like the action and reaction pair. So in many cases, finding out these action and reaction force would be very difficult. But we could simplify the scenario by neglecting the internal force, but just to consider the momentum. But we are not working on the linear momentum. We are working on the rotational form of the linear momentum, and that is what we call the angular momentum. So that is what we are going to see in today's lesson. We would try to apply the concept of an angular momentum and use it in various situations. To start with, we have to kind of define what it is the angular momentum. Now, let us start by thinking of a particle. This particle is moving in a circular orbit. So it is performing some kind of a rotational motion. The object, it is subjected to a force, a tangential force. So this tangential force acting on the object at a distance r from the axis of rotation, of course, you would understand that it would generate a torque. So the torque, according to our definition, is R cross F. That is the vector notation. So for the time being, we just write it as it is, R times R cross F to generate the vector of torque. And if you remember that in a linear motion, the force is actually defined not equals to, strictly speaking, not equal to ma, but equal to the what we call rate of change of linear momentum. Rate of change of linear momentum. So if we rewrite the force to be the rate of change of linear momentum, then the things would change in a very subtle way. Here, the torque becomes R cross dp over dt. P is the linear momentum, m times v. M times v is the linear momentum. Now, we try to add a term which, just for convenience, we add a term which sometimes it becomes useful later. We try to add a term, dr over dt cross p equals to 0. With that, for students who have experience with the differentiation, they will recognize that this term, when added to the first one, it would be leading to a factorization, because the R cross dp over dt plus dr over dt cross p would be equivalent to the differentiation of the cross product R cross p. Now, we have no idea at the moment, physically, we have no idea what is R cross p. But when we refer to the equation form, we could see that the torque, remember, it is the rotational version of the force. The torque, it is equal to the rate of change of this term, R cross P. P, once again, is the linear momentum, m times v. So just to type it here, P is equal to mv. Of course, we cannot, well, I cannot write the arrow, or actually I can, kind of. Okay, like that. P is equal to mv. So we have now a equation form that looks once again like the definition of the force in the linear motion. In the force, it is equal to the rate of change of momentum. In the case of torque, it is equal to the rate of change of this term R cross P, which we would call it the angular momentum. The angular momentum. So this angular momentum is defined as R cross P. The L, which is the angular momentum, is equal to R cross P. All of them are vectors. All of them are vectors. So what does R cross P mean? At least in the mathematics, what does that mean? Now, if we go back to the case of the cross product that we have seen before, where we've seen it actually a few slides ago, if I remember, the torque equals to R cross F. So mathematically, the cross product, A vector cross B vector, the magnitude would be equal to A times B times sine phi. Or here, the magnitude is R times F times sine phi. Phi is the included angle between the two vectors. So going back to the equations at here, the magnitude of the angular momentum would be equal to the magnitude of the two vectors, R times P times sine phi. Phi is the angle included. Phi is the angle included between the P vector and the R vector. Now things would get very abstract from now on, but let's try to figure it out in a more realistic way, or a way that is more easy to visualize. P, once again, is the linear momentum. So we are considering, if you like, the product of two things. It is the product between the P vector and the R sine phi. What is R sine phi? Turning this diagram 90 degrees, and if you view it in the XY plane, sorry, the drawing would be a little bit difficult, but let's try to do it. Now we are viewing in the X, from the top, XY plane, X and Y, okay. The P vector is moving along this direction. Sorry, I have to draw it. Sorry, that is a P vector. Unfortunately, I cannot change the color. Okay, that is a P vector. And the R vector, it is pointing like this. Document. The R vector is like this. I hope the diagram is something you could visualize. This is R vector. Okay, now P vector is at here. I may try to actually, well, okay, let's do it like this. P vector is this vector. R vector is this one. So the angle phi is this one. The angle phi this is the phi angle. Well, you try to extend it, and this is the phi angle. R sine phi is this distance. This is R sine phi. What does it mean? Once again, it's the product between the P vector and the perpendicular distance between the P vector from the axis of rotation. So you could group it like this. It is R sine phi times the P vector. The product between the linear momentum and the perpendicular distance of the angular momentum from the axis of rotation, perpendicular distance only. With that, we could actually understand quite a lot of questions already. Now, once again, the definition of the angular momentum in mathematics, it is equal to R times, in the mathematics, the angular momentum is R times P times sine phi. If it is generating a rotation in the anti-clockwise sense, we can classify it as a positive angular momentum. If the momentum is causing a rotation in the clockwise sense, then it is a negative angular momentum. The equation form is R times P times sine phi. The magnitude and the direction, of course, depends on how you choose the axis of rotation. That means it depends on where is the origin, of course. So the idea of the talk is that it is equal to the rate of change of this quantity, angular momentum. So far, we have been talking about the deviation of the angular momentum. Excuse me, Mr. Choi Waiting or Miss Choi Waiting, would you please turn off the microphone, turn off the mic? I have been helping you to turn it off for a few times. Yes, thank you. So, okay, now I get lost if I get distracted. Now, okay, once again, we have been talking about the angular momentum by considering one single particle. We are talking about one particle only. And this particle is under the influence of a force. Of course, if the particle is at a distance r from the axis of rotation, this would become a torque. And we have in this way defined the angular momentum for one particle. What if you have a collection of the particles? Of course, you would be adding up the angular momentum, just like the case of multiple objects moving in a linear way. You would add up all the momenta together. But before that, let us try to figure out what it actually, what is the implication of this angular momentum. So here you have the angular momentum of a particle in a circular motion. As an example, this particle is just the one we have seen. It is moving in a circular orbit, radius r, and the example asks you about the magnitude and the direction of the angular momentum relative to an axis through the O when its velocity is v. If the object is moving in this fashion, it is moving in a circular orbit, then the velocity vector is always perpendicular to the r vector. Include the angle phi in this way. In this way, it is equal to 90 degrees. This is equal to 90 degrees. And the angular momentum in this case, which is equal to r times p times sine 90 degrees, it becomes r times p. P is the linear momentum, m times v. So it becomes mv times r. So for the particle rotating in a circular orbit, the angular momentum is actually constant. No matter it is here or here, okay, velocity keeps changing because the direction keeps changing, but the speed is constant. And also it is always perpendicular to r. So the angular momentum of an object moving in a circular path with a constant speed, it is a constant value. The angular momentum would be a constant value. Once again, this is the case of a single particle. What if you have a collection of the particles? Now, let us skip the example 11.4 for the time being. We just go to the definition of the angular momentum for a rotating rigid body. Linear momentum and velocity directions are the same, yes, because linear momentum is m times v. M is a scalar, velocity is the vector. So linear momentum and velocity points the same direction. Velocity or the speed, well, it depends on whether you are trying to extract the scalar or the vector. Of course, here it is the velocity, which is a vector. And in this equation, we are calculating the magnitude. We are calculating the magnitude. So this one, this one, we are calculating the magnitude. So this one, v at here becomes the speed, because we do not care about the direction anymore. Well, actually, we are not considering it only. We are considering only the magnitude. So the speed is sufficient. Okay. Right. So for a single particle, it is the product of the is the product of the r vector and the linear momentum. What about a collection of particles? Well, fortunately, for a collection of particles moving in such a way, the angular momentum could be calculated fairly easily. We have just seen in the example 11.3 that the angular momentum for one particle, it is equal to mv times r. So for any of the particle on the rigid object, it has the angular momentum equal to mvr. And it is not deforming the object, so it is a rigid body. They are performing a perfectly circular motion all the time. So it is always mvr on a rigid object. Adding all the particles up, what would you have? Let us add them together. R times m times v. V, on the other hand, is related to the angular speed by omega r. So it becomes mr squared omega. Once again, all the particles in the rigid body rotate with the same angular speed. Therefore, it becomes mr squared bracket times omega. This term in the front is the moment of inertia. So it is equal to I times omega. Notice once again the similarity. In the case of the linear momentum, L, which is a linear momentum, is m times v. In the case of the, I should not type it this. It is the linear momentum, P is equal to m times v. In the case of an angular momentum, L, it is equal to I times omega. Notice the similarity between the two equations. M correspond to I. One is a linear motion, one is rotational motion. V correspond to omega. One for linear motion, one for rotational motion. So this is the idea of the angular momentum for a rotating rigid object. Okay. Now, let us go back to the example 11.4. We have to talk about it because we need to include both the single particle and rigid, rotating rigid object in the example. So let us take a look at the question first. What is the L equals to mr squared omega in the equation at here? It is the moment of, it is the angular momentum for one particle on the object. Of course, you do not have one particle in a rigid object. You have many particles. So you start with this one and then add them all together. Now, in this example, we have a system of three objects. M1 is falling under gravity, but it is held back by the string. The string is moving over a pulley, and the spokes of the pulley, that means the lines that goes in the radial direction, the spokes of the pulley have negligible mass. The mass of the pulley, therefore, is concentrated at the rim. The circular part only has the mass. So this would give you some hints about its moment of inertia. mr squared, moment of inertia. Let me try to write it. The moment of inertia, I is equal to, by definition, the sum of mr squared. If all the masses are at a distance r from the axis of rotation, then it will be some, well, originally it is mi squared, but now it becomes mi times r squared. R is the same for all the particles, so it becomes r squared times some mi, which is actually the total mass. So that is why you have the total moment of inertia for the wheel equals to mr squared. Now, what is this in this question? You are considering that the object is the objects are connected to one another, and they are connected, of course, by a string. The external torque acting on the system, the external torque acting on the system would generate a rate of change of angular momentum. Just like the case, the force, it is equal to the rate of change of linear momentum. So that is in this question asking you to find an expression for the linear acceleration of the two objects, m1 and m2, by the concept of the torque and angular momentum. So the torque and angular momentum, by definition, they are related in this way. What is the torque acting on this system? The whole system, let us consider the whole system is rotating about this point. The axis of the wheel. What is the torque possibly acting on about this wheel? In fact, there is only one external force acting on the system, and that is the weight. That is the weight of the mass m1, which is pointing downward. So that is m1g. And assuming this is a particle, it is right underneath the string. So the force is in this direction. The perpendicular distance now becomes important. The force is in this direction. Let us translate the force. The perpendicular distance between the force and the axis of rotation is r. So the left-hand side is the torque, m1gr. Once again, force is along the vertical direction. The force, it is along the vertical direction. I use the arrow along this vertical direction. And it is at a distance, it is at a distance r from the axis of rotation. The tension, it is not the external force. It is not the external force. It is the only external force that would be acting on the whole system. It would be the weight acting on a mass 1. So even for the M2, it would be balanced by the reaction force. So there would not be any torque generated by M2 about the wheel. So there is only one possibility. What about angular momentum? Now, this is tricky. The linear momentum first for the particles, linear momentum of the particles M1 and M2, well, okay, they are blocks, but let us consider they have the linear momentum and they are particles. It is equal to m1v times r. Remember what is the definition of the linear momentum? m1v. And the angular momentum is the product of the linear momentum and the perpendicular distance from the axis of rotation. So that is m1vr. Similarly, for the particle 2, which is, let us consider to be attached to the string like that at the center of mass, it would be m2vr. Finally, you have the pulley. This pulley would be moving in a rotational format. And so you have the angular momentum, which can be calculated by I times omega. What is I for the wheel? You have, just as I explained, all the masses focus on the rim. So it would be mr squared. Okay, another time, Mr. Choi. Sorry. Oh, Ms. Choi. Yep. So it will be mr squared for the I. Omega, it is related to V and R. So V over R. So that is why we have on the right-hand side the equation like this. R changes to R because it is pulley. If it is a disk, can it still be R? Well, if it is the disk, then the moment of inertia would not be simply mr squared. We may have to use, for example, 1/2 mr squared because the mass distribution would be different. In any case, here in this equation, there are many terms which are independent of time. R is independent of time, M is independent of time. So you could all take them out. Only term that could depend on time is the velocity. So dv over dt, which is acceleration. So you could use a fairly simple method to find out the acceleration. Okay, if you are not convinced, let us do it in the way that we know. We use the torque and angular acceleration approach. This is something we are more familiar with. Here you have three separate particles or objects. The first one is M1, second one M2, finally the pulley. For M1, it is acted on by tension 1 as well as the mass, as well as the weight. So you have the equation like that. For the pulley, you have the torques generated by the tension. Now, be very careful. The pulley would not be smooth because if it is smooth, there would not be frictional force. And this would not cause any rotational motion. Just the tension in the string would not cause the rotation. You need to provide some kind of a frictional force. But in any case, this would be represented in the way of a tension in the string. So the tensions in the string would be causing the net torque that helps the rotation. And this tension must be different because if they are the same, there would be no torque to generate the rotation. Finally, you have the T2 that accelerates the particle M2. So three equations altogether, you will find out once again the acceleration of the whole system. They should have the same acceleration in the linear way as well as in the rotational way. So that is the example of using the angular momentum to solve some problems. And before the break, let us take a look at another example. And this is the bowling ball, which we assume it is a sphere. So the moment of inertia for the sphere about the center of mass can be found in the table at page 27. So you go back to page 27. The moment of inertia for a solid sphere about its center of mass, it is 0.4 times mr squared. So let's come back. 58. it is spinning at 10 revolutions per second. So you could calculate what is omega. 10 revolutions per second, it is equal to 10 revolutions per second times 2 pi radian per revolution, because you want the angular speed to be in radian per second. So 1 revolution is 2 pi radian. Moment of inertia, 0.2 times m times r squared. Radius is 0.12 meters, and angular momentum I omega. So this is just a straightforward application of the concept, moment of inertia, as well as the angular momentum of a rigid rotating object. Okay. Okay, now I would take a break about 10 minutes, and after the break, we would be going through the conservation of angular momentum, and we would take a look at some tutorial questions. And let me try to organize a bit at here, just to give you some warning. You would notice that in the course information, there is a teaching plan. And according to the teaching plan, we would be having the test. The test would be on the 19th of October, which we would still keep this date. So the test topics would be up to what we teach today. So we would be testing up to unit 11. We will be testing up to unit 11, up to angular momentum. So the format of the test, as well as the equation, is they would be provided to you later within this week. But please start the revision. You are covering quite a lot of the topics, especially the later topics, the rotation and the angular momentum. They are quite new to you. So please take some time to do the revision. And another thing you should notice is that we have the assignment 1.3 and 1.4, which are due today. And after today, I would be releasing assignments related to rotational motion. So we would be setting a deadline for those assignments on the 19th, for the 19th. I don't really think that past papers are useful, partly because in the past, we asked the students to write down all the equations, but this time we would not have any chance to do that. It would be quite close to what we do in the assignment. And in any case, the questions are firstly similar to the examination, and secondly, the exam questions are available on the exam database of PolyU library. So you can just go to the library website to download those question papers. And if you are still lacking questions to practice, once again, university physics textbook have more than enough questions, I believe, for you to practice. So please make use of these resources. Okay, some of the classmates are asking about the answers for the quiz on Monday. So I'm showing you the numbers at here, the answers at here. What I believe actually is that it is more useful for you to understand how to do the calculations rather than checking whether the answers are correct. It depends on what is the relative sense of the okay. The tutorial questions, well, I don't know what you mean by similar. Well, they are structural questions. So in that sense, I think they are similar, but well, I would not say that we would just change the numbers and then you would work on the same question. We have infinitely different ways to test the same concepts. So why is the work done negative? It is because you apply the force to slow down the motion. So the force and the displacement would be in a negative sense. So the work done in that case would be a negative number. We have been announcing the test for a long time. So no, we would be following the same schedule. What suggestions for the test? I don't know. Do more exercise. Try to work on the questions in the free textbook. There are a lot of them for you to practice. So, okay, I would take a break about 2 minutes before I start the lesson again. For the question of last quiz, I actually do not have the solution on hand, well, the full solution on hand, because that is some templates prepared by other colleagues, but I could help to write down some and post it later. Okay. Right. In any case, let's come back to the lesson. Now, we have just before the break talk about the angular momentum, and we have two separate cases. For individual particles, it would be the product or the cross product of the r vector and the p vector. P is the linear momentum, and r is the distance from the axis of rotation. So it would be equal to rp sine phi. It will be equal to rp sine phi. Basically, it is the product between p and the perpendicular distance of the p vector from the axis of rotation. On the other hand, if you have a collection of particles that are rotating in the same circular orbit, in the same circular track, then all of them would be having the same angular speed. So you could add them up together. At the end, for a rigid object, the angular momentum would be equal to I times omega. I is the angular moment of inertia. Okay. Now, the idea of the torque is equal to rate of change of angular momentum would be kind of related to what we have seen before in the linear case. If you have no external torque, if you don't have no external force, there would not be any change of the linear momentum. Similarly, if you have no external torque, acting on the object or on the system, there should not be any change in the angular momentum. So when the external torque is equal to 0, then dl over t is a 0. L would, in that case, become a constant. So the angular momentum of a system of objects should be kept constant. And that is another conservation law, the conservation of angular momentum. Just like the case when you have no external force acting on two objects, all the forces become internal, there is no net force. In that case, linear momentum is preserved. In the angular case, when there is no external torque, the total angular momentum would be conserved. And this would become very useful when we consider the rotation of objects. Now, this may not be very obvious in the case of a linear momentum, because we actually avoid a lot of problems with changing mass of objects. Linear momentum is equal to mass times velocity. So it could actually be a mass of objects that is changing, but most of the time we do not have it in the real situations. On the other hand, angular momentum could be changed. Angular momentum is conserved, but the changes could be brought by a change in the moment of inertia. Here is an example for such a change. Well, this is just the pictures. Let us try to find something on the internet. Okay, YouTube is always our favorite. So you see, of course, we are seeing the person that is spinning, but this is important in the last two moves. So when the person extends the arm, it is spinning at a certain speed, but when she puts the arms close to the body, you see the spinning is actually going faster. The video does a better job in explaining the things than I do, I believe. So let us try to take a look. So angular momentum conserved. When R decreases, the spinning speed increases. So when she holds the arm close to the body, as you will see, okay, let's come back to the notes. When hold the arm close to the body, part of the mass would be having a small radius of rotation compared with the other case. So in the case on the right-hand side, the arms are extended. So these masses of the arm would be far away from the axis of rotation. So the moment of inertia is larger. Here, because the arm is close to the body, the mass of the arm is close to the axis of rotation. So the moment of inertia gets smaller. By the conservation of angular momentum, we could see that for the same quantity I times omega, when I is small, omega gets larger. And that explains why when the skater puts the arm close to the body, he or she spins faster. There would be no net torque. We assume that there is no net torque acting on the skater. So the conservation law can be applied. And well, of course, that is just a quick description. We will see some examples later. But just to summarize what we have seen in the topics that we have discussed so far, there would be conservation of energy for an isolated system. So initial energy is equal to the final energy if there is no work done by some external force, or no energy transfer across the system boundary as that is described typically in the physics textbook. Secondly, the conservation of linear momentum if there is no external force acting on the system. Finally, if no external torque acting on the system, then the angular momentum would be conserved. These would be the usual conservation laws that we have to use. Now, let us take a look at some examples before we go to the tutorial questions. The first example is a kind of a toy in a place called the playground. Well, not sure how familiar you are towards the things or towards the term playground. This is a kind of a place where kids at least my age would go to kill some time. These days you kill the time on the mobile phones. In the past, kids do not have the mobile phones. They go to the place called the playground. And in the playground, there is a kind of a toy called a merry-go-round. There are much more sophisticated versions these days in the theme parks. For example, in the Disneyland, they have the merry-go-round as well, where you ride on the horses, for example. But in the old days, the merry-go-round is basically just a metal plate spinning on the axis, and that's it. People could spend days on it, just try to hold the merry-go-round as if it is their own territory. Wow, yeah, as I said, when you type merry-go-round, it will show you anything that is spectacular rather than simple ones. But the one that is shown, yeah, it will be more like this one. The one shown in the PowerPoint slide will be more like this one. So, and here, the merry-go-round is basically just a metal disc with a metal disc that is a platform, and the mass is 100 kg, radius is 2 meters. And then you have a student initially at the edge, and then gradually he will be walking towards the center of the merry-go-round. So assuming that there is no external torque acting on the whole system, all the forces of the torque would be internal. Therefore, the conservation of angular momentum should be applicable. So let us see what are the moment of inertia. Initially, it would be the moment of inertia of the platform plus the moment of inertia due to the student. It is a metal disc rotating about an axis going perpendicular to the plane. So the equation we use in the page 27, it would be close to this one. Wow, use a little bit of imagination, please. Consider this cylinder to have a very short thickness. So in that way, it becomes a disc. And it is rotating about the center of mass. You do not need to go to this one. You do not need to go to this one. You could go to this one. And let's try to go back. 62. Yeah. So it is 1/2 mr squared. And then the student is at a distance r, because at the beginning he is at the rim. So mr squared. He has all the mass focused at the edge of the platform. So mr squared. Finally, he would be moving to a point 0.5 meters from the center. So later, his contribution to the I becomes m small r squared. Initially, the disk is rotating 2 radians per second. So the initial angular momentum is the initial I times the initial omega. Finally, it is the final I times the final omega. So with that, after fitting in the numbers, it would become 4.1 radians per second. So angular momentum is conserved because there is no external torque. We assume that there is no torque acting on the system as the rotation is on a frictionless axis. But we would also need to see whether energy is conserved, because when the speed, the rotational speed changes, the kinetic energy associated with it should change as well. So what is the change of the kinetic energy? Initially, it would be 1/2 I omega squared with the initial I and initial omega. It is 880 joule. We have the numbers in the question. I is in the question. Well, I is here. omega is 2 radian per second. So we calculate it. Finally, it would be IF omega F squared. It becomes 1,800 joules. Seems that energy has been gained. Energy has been gained in this case. So why? Why there is an increase in the energy? Well, the only possibility is that the student is walking from the edge to the center. So in that way, he has contributed his energy in order to cause the increase of the kinetic energy of the system. So it must be coming from the student when he walks towards the center of the platform. So that would be the justification for the increase in the energy for the whole system. Here is another example. This one will be quite difficult. So we try to go through it very slowly. The physics would be difficult in the beginning, and later it will be the mathematics that is quite tedious. But we would first go through the mathematics. Well, the student is contributing to the energy because he's walking. When he walks, he is in a very implicit way contributing his work done to the energy of the system. So here we have a disk and stick system. Initially, we have the stick that is held in along the y-axis, if you like, and the disk is moving along the x-axis with an initial velocity vdi. The whole system, the disk and the stick, they are placed on a frictionless ice surface. So there is no frictional force acting on the disk and the stick. So no force, no torque. And when the disk hits on the stick at the end of the stick, it causes the motion of the stick. The motion is like this. The stick rotates. Eventually, it rotates about its center of mass with a constant angular speed omega. And at the same time, the center of mass would be moving with a linear speed vs. They are independent of one another. It is not rolling. So do not identify omega with vs. They are not related to one another, as in the case of rotation, as in the case of rolling. They are separate. They cannot be related by the simple equation. And by some miracle, the sphere, the disk, keeps moving along the same direction, but with a different velocity. So at here, we would have to find out the final speed of the disk, the center of the speed for the center of mass of the stick, and the angular speed of the stick after the collision. And here we assume the collision to be elastic. So the whole problem can be considered by the conservation laws. You have a number of conservation laws. First, conservation of linear momentum. Second, conservation of angular momentum. And finally, because the collision is elastic, it would be the conservation of energy. First, conservation of linear momentum. The disk is moving initially with VDI, so MD VDI. Finally, it moves with a DF, so MD VDF. At the same time, the stick would be having a center of mass moving horizontally as well, so MSVS. Second, it would be the angular momentum. Now, this would become very tricky. We consider the angular momentum for the axis about the center of the rod. The angular momentum for the disk about the center of rod, it is V R times M times VDI. So it is the R times the linear momentum. It is going in the clockwise sense, so it is negative. And then after the collision, it moves with the same direction. And even the center of mass for the stick is moving. It is at the same perpendicular distance. Now, you have to be very careful. Here is the direction of motion for the disk. The perpendicular distance between the center of mass and the red line is still here, which is still R. The perpendicular distance is still R. So it is still R times MD times VDF. So of course, you can argue that it is R times P times sine phi, but R times sine phi is the perpendicular distance. In this case, the perpendicular distance has not changed at all. So it's still R times the linear momentum of the disk after collision. At the same time, for the rotational motion of the stick, it has the angular momentum I times omega. We are writing it as this way because later we could justify the writing by having the omega being negative, as you will see later. But first, let's just have a I omega as the angular momentum. So that is the equation for the angular momentum conservation. Finally, conservation of energy. Kinetic energy of the disk is equal, at the beginning is this one. Finally, it is, wow, once again, we do not know the exact direction of omega. Only after we calculate it, we know. If it is positive, it rotates anti-clockwise. If it is negative, it rotates clockwise. Okay? Now, kinetic energy of the disk after collision is this one, of the disk. And the kinetic energy, linear kinetic energy of the stick is this one, about the center of mass. And then the rotation about the center of mass would have the rotational kinetic energy, 1/2 I omega squared. So at the end, these are the three equations that we need. The rest of the calculations would be mathematics. So in a certain sense, we are not quite interested to know, or at least I am not quite interested to know how to figure out all the complicated calculations. These are all mathematics, factorizing the terms and moving around the equations. They are manageable with some patience. At the end, I would be more interested to know about the final answers for the velocities of the stick as well as the angular speed of the stick. The stick velocity is 1.3 meters per second, meaning that it is moving to the right at 1.3 meters per second. The center of mass is moving 1.3 meter per second. For the disk, 2.3 meters per second. It is slowed down because initially it moves with 3 meters per second. Omega, as you will see, minus 2 radian per second, meaning that it is in the rotation in the clockwise sense, which is reasonable because the initial angular momentum arising from the disk would cause a angular momentum in the clockwise sense. So the angular momentum in the final situation should be in the clockwise sense as well. So the stick is rotating in the clockwise sense. Therefore, you have a negative value. Now, we try to compare various terms in the table at here. It is not much used to directly compare the velocities, but it is very important to compare the linear momentum, the angular momentum, as well as the total energy. Linear momentum before collision, it comes only from the stick. And then after the collision, it is distributed between the stick and, well, at the beginning, it only comes from a disk, only comes from a disk. After the collision, it comes from the disk as well as the stick, but it is conserved. Angular momentum, initially, it comes from the stick moving about the center of mass of the stick. Well, sorry, once again, it's very confusing. Initially, the angular momentum comes from the disk rotating about the center of mass of the stick. After the collision, part of the angular momentum from the disk would be provided to cause the rotation of the stick about the center of mass, but the total angular momentum is still the same, minus 12 kg meter square per second. Finally, total energy. It is elastic collision, so initial translational kinetic energy becomes partly translational kinetic energy of the disk and the stick, and partly becomes the rotational kinetic energy of the stick. So these are direct comparison of the energy terms. And this would be the important concepts related to the rotational motion. So we have some time left, so it would be good for us to take a look at the tutorial questions. Let us take a look at 2 tutorial questions. Okay, you will be here. Let's take a look at the question number 7 and number 8. Some of the students ask about the merry-go-round question. How is the walking related with the work done? Well, it is an internal process, really. You have the person walking on the platform. So the situation is kind of complicated because when you walk towards the center, you actually have the person changing the speed from time to time. And there would be a force in order to change the speed. And therefore, there would be some work done when you are moving from the edge to the center of the system. So it would be a fairly complicated scenario, I must say. Right. So in question 7, you have a cylinder with moment of inertia I1 rotating with a VI. And then the second cylinder with a moment of inertia I2 and initially 0 angular speed drops on the first one. So it becomes a collision, if you like. Eventually, they move with the same angular speed. Eventually, they move with the same angular speed. So you're asked to calculate what is VF, well, omega F. The situation is actually quite straightforward, if you like. So let me try to show you the calculations. Let me see. Just a minute. Okay. Now, here is the solution of the question. You have the 2 disks. Initially, the disk I1 moves with an initial angular speed, omega I. So on the right-hand side, it is I1 omega I. And then on the left-hand side, because it is an internal system, so all the torques are internal. So I1 plus I2 times omega F is the final angular momentum. And just like the case of a linear motion, this would be an equivalent of the inelastic collision because they are finally moving with the same angular speed. And in the second part of the question, you are asked to demonstrate that the KE, the kinetic energy of the system, decreases as a result. Just write down the equations for the kinetic energy. Initial one and the final one. So writing down these two equations are quite straightforward. And the ratio of the kinetic energies can be compared at the bottom. So Kf over Ki, by some manipulation of the terms, it would be I1 over I1 plus I2. Very obviously, the energy has decreased because the ratio is smaller than 1. Of course, you could you could consider the energy loss to be due to the need to overcome the friction and causing them to move in the same angular speed. Okay. Now, some of you asked in the chat, in the previous question, how is the disk still contributing angular momentum when it has detached from the ice after collision? Are you talking about the example in the lecture notes? If you go back to the lecture notes, let me see. If you go back to the lecture notes, let me try to. Go to the lecture notes. Well, I don't think it is actually detached. It is still the whole system sitting on an icy surface. I'm not sure if that is something you're asking about. Let me see. Yeah, the whole system, they are just sitting on the ice surface. And you have the axis of rotation, which is the center of the rod. Whenever you have the object moving about the axis of rotation, they contribute to the angular momentum of the whole system. That would be probably what you're asking for. The angular momentum is about the axis of a rotation. So the disk, because it is still having a component of the velocity moving, and at a distance from the axis of rotation, it will still be contributing to the angular momentum of the whole system. After the collision, the disk is not, we are considering the disk to be actually a point particle, so it does not rotate by itself. And after the collision, you mean the stick or the disk is not rotating? Okay, maybe you could ask me after the lesson. Let's try to figure out the question number 8 first in the tutorial question. Well, this one is quite similar. On surface, quite similar to the example, but there is a very, very important difference between the two situations. And that is, let me try to move it like that, okay? And that is the rod, instead of freely movable on an IC surface, it is now fixed at the center. It is fixed at the center, so it can only rotate but cannot move in the X and Y direction. So let us try to take a look at the question. You have this projectile, basically a disk, moving with speed vi, and it strikes the end of the disk. And striking the end of the rod or the stick. And the stick is pivot about a frictionless axis perpendicular to the plate. So because it is frictionless, it will not provide any torque. Therefore, the rotational motion would not have any external torque. It would follow the conservation of angular momentum. On the other hand, because the stick is fixed, so it would provide the horizontal or vertical force that prevents any motion in any of the horizontal or vertical direction for the center of mass. Therefore, linear conservation, well, conservation of linear momentum may not apply in this situation. It may not apply in this situation. So you have to be careful in this case. Now, let us take a look at the various parts. We wish to find out the fractional change of the kinetic energy in the system during due to the collision. So initially, the particle is moving, so it has a linear kinetic energy. Finally, the particle sticks to the end of the rod, so it would rotate together in elastic collision. Okay, now, is the system isolated or non-isolated? The system is not suffering any external torque or force. So the collision by itself should be isolated. The system itself should be isolated. And what is the magnitude of the angular momentum of the whole system before the collision? Angular momentum at the beginning, it is contributed only by the particle moving horizontally. So once again, the momentum vector is in the x-axis, perpendicular distance d/2. Therefore, the angular momentum is mv times d/2 at the beginning. What is the moment of inertia in the part C? What is the moment of inertia of the system about the axis through O after the projectile gets stuck to the stick? The moment of inertia of the stick about the center of mass, you have it in the lecture notes once again, page 27. About the center of mass, the moment of inertia is 1/12 md squared. Go back. Well, whether it's isolated or not depends on whether you have a any external force that could change the motion. Here you have the rotation that is not acted on. You have a rotation that is not acted on by any external torque because it is frictionless. So you would have an isolated system. The linear momentum, well, at the beginning, let us put it this way. Right during the collision and right after the collision, it can still be considered to be conserved. But unlike the situation in the tutorial, in the lecture notes, the center of mass cannot move. So in that way, you would not consider it to be free from the action of the force. So the rotation after the sticking, you could still consider it to be isolated because it is not suffering from any external torque. Typically, we do not consider the gravity because we have the collision, which the impulse or the rate of change of the momentum would be very large. The impulse would mean a force to be large compared with gravity. So gravity typically is not considered. Okay, let's go direct to the solutions, maybe, just to save a bit of time. Okay, so after the collision, the total moment of inertia it would be 1/12 md squared 1/12 md squared plus m times d/2 squared. So that is m d/2 squared. The center of mass for the rod is at O. Center of mass of the rod is at O. Of course, when you stick the particle at the end of the rod, the center of mass of the whole system may change, but the center of mass of the rod is certainly still at O. And then in the D, if the angular speed of the system after collision is omega, what is the magnitude of the angular momentum of the system after the collision? Well, it can be quite straightforward to see. It's total angular momentum times omega. So it's an answer of C multiplied by omega. Afterwards, it would be, you see, and we remove it. Okay. Afterwards, it would be E, angular speed after collision. Angular speed after collision. So by the conservation of angular momentum, we could find out what is the angular speed after the collision. Once we know the angular speed after the collision, we could compare the energies before and after collision. Before the collision, Of course, it is 1/2 mvi squared. After the collision, it is just the rotation of the whole system. 1/2 I total. This is the answer from C. And then omega squared, answer from E. Looks a bit complicated, but it seems it can be factorized. So comparing the energies, the change in the mechanical energy is delta K at here. And the fractional change is m over large M plus 3m. So it is reduced according to the masses of the particles. Okay. And in any case, it has been reduced due to the inelastic collision. Well, there's no reason. You and I have seen the calculations why 3m. It comes from basically here, I think. We are not saying the factor to be 3, multiplying the m by 3. We did it by calculation. So sometimes you could just follow the calculation steps and answer some of the questions. Okay. Now, once again, like the lesson on Monday, I have posted a small quiz on the Blackboard, on the Learn at PolyU. So if you go to Learn at PolyU, see, if you go to Learn at PolyU, in here, content, in-class quizzes, you will see that the quiz today is already available. So you would have 30 minutes to finish the quiz. There are actually 2 questions that I have broken actually from one single question that have 2 parts. But it is difficult for me to set the quiz to have 2 parts. So I break it down into 2 questions. So it spends about 30 minutes and you have 3 attempts. You will have 3 attempts to do it. So please take your time to do it. You have until the end of today to finish it. Okay. So in this way, we will finish the teaching of the rotational motion. And from next week onwards, we would be talking about the equilibrium as well as the some other types of motion. Okay. What is L rod? Okay. Right, maybe I would stop the lesson at here and try to answer the questions from the students. Okay, thank you very much.